All right. Yep, it's. So welcome back from lunch, everyone. And this is today's final session before we go to our social event. So to kick us off, we have Yung Ahn, who will say something about the Nax Programming. Take it away.
A lot of people seem to be sleepy, but not here. So does this one work?
Do you want the?
No, I'll just do it here. It just works well. So my name is Yung, and I will talk about the Nax Programming language. So as you see, there's subtitle. I just finished this slide this morning, so there's some the template there, but the content is pretty much there. So the motivation of the new language design is about so-called lightweighted approach. You program in programming languages, but to have dependent types, not real dependent types, but in lightweight dependent types with phase distinction. And so it works pretty well, and we can do useful things in practice, but can we make it better is the main motivation. And we'll talk about the outline of our approach and what people and we have done, and talk about the Nax programming language. So the motivation is that when we have rich enough types, we can express and maintain fine-grained program properties, like simple things like length of lists to pretty complicated things like type-preserving compilers. And the most loved way of doing it was JDP extension in Haskell. So the expectation is that you may need less effort verifying certain kinds of verification problems, because if you use formal proof assistance, you would have to program in a different language, and it's not a real programming language, and you do want to have a real implementation without going through some magic of what do you call it, extraction and other things. So it definitely has gained popularity over the past decade, but there are some shortcomings that we think we want to have, and it would be nice to have. So one of the shortcomings is that there isn't really a formal correctness guarantee, as in, say, theorem provers, because it's really this semi-formal confidence you kind of have, believing in yourself that you haven't used anything wrong, including infinite loops and those kind of things to inject inconsistency in your proofs about program properties. So, I mean, if you have a loop equals loop in Haskell, you can prove falsity because it can be any type for all A to A. And, oops, yeah, this is the problem. Just press end. And this has been addressed recently, but another problem is that term structures are duplicated at type level. And it's not a real term. If you want to model something like a vector or left index list, and you want to index n as the length of the list, and there's obvious typo, it's a vector of AI0 there. But what you end up doing is making a copy of the 0 and a successor in the type level, and there are several problems. If you want to have any kind of functions on integers, you have to write once more again on the type level. If the type system supports it, and well, in GHC they support it by type families right now. But anyway, you have to duplicate the code. That's the first problem. And the second is that the semantics is not really that precise because you can't prevent things like successive bull and those things. And, well, the other well-known problem is type inference, and papers on GHD type inference is being published every year. And still, it's not that obvious that, I mean, it's obvious that we do need type annotation because it's not possible. But how much and where exactly we want to have is another design issue. So the outline of our approach is to first formalize the idea of real term indices, which has type phase distinction. We call it traceable term indices. And, well, of course, term can appear in types, but with phase distinction. And also study, we need to, if we want our language to be used as really formal logic, we should have some kind of induction principle or principal recursion schemes that surely terminates. And so we use the Mendler style recursion schemes, which we'll go through briefly and later. And also, we want to design a new programming language to address the last issue of usability, like type inference. And yes. So, but it's not yet a real programming language because the only implementation we have is the logically consistent, which means it's also strongly normalizing. So it's not a Turing-complete language, but there are some ideas of how to add non-logical features in the Trellis project group, which we are participating in. And that will be our future work. So, first, I should explain what Mendler style recursion containers is. If you haven't seen it, well, I think if you have seen the Oxford style, or it's usually called squiggle style, and it's the thing that most functional programmers write. Well, not most, because I already split it down the recursion operator mu. So if you want to iterate over a structure that is recursive and its shape is f, and its recursive type is a fixed point of that, you have to have this phi function that maps from f to a. Then you can calculate functions from the mu f to a. So, and this definition is polytypic, and that's a polite way to say it's ad hoc. Which means that you have to define fmap for each type. You can automatically derive it, but you have to write it down, each different instances of it. And when you want to reason about why this is terminating, you have to rely on some meta properties about that. You should believe that this functor f has nice properties that makes this inter function always normalized. This is Haskell code, of course, so there's laziness, but if you don't throw in any other general recursion, and if you think this is just a lambda calculus rewriting, then this should terminate because functor has some nice properties. And there is this equivalent, somewhat equivalent formulation that does pretty much the same thing, and it's called the Mendler style formulation. And you look at it, it looks pretty similar, except that it doesn't use fmap, and the definition is polymorphic. And people who know about category theory a lot just says that this is some kind of time extension or something like that, but well, I don't understand very well. So what I like it about is that it's a polymorphic definition. Well, it does use higher rank polymorphism, but it's uniform in any f, any function. It doesn't even have to be a functor. So now you don't have to know or have beliefs in category theory or whatever. You just have to believe system f omega. And
is this worse or better?
So, and it also immediately generalized to higher primes. So the Oxford style does generalize to higher primes with default and defaults. There's ins and givens, and we'll work on this for nested data types. So you do need a little bit of thinking, but in Mendel's style, you don't even have to think. You just rewrite the types into higher order arrows, and it just works with exactly the same definition. So there are catamorphisms, if you have heard about it, histomorphisms, and some strange morphisms in this Oxford style. But there are several combinators in Mendel's style as well. So how this, so for example, there's an iteration which can do full, basically. You can call recursive call, like do the length. And there's a primitive recursion that we can call things recursively as well as get the value and operate it with them together. And there's also a course of values version of iteration and primitive recursion. The course of values is Fibonacci function is well known, and we've seen that in the last session that you can kind of rewrite this into iteration. You didn't set that, but that's what was basically going on. And there's also, of course, the values primitive recursion. This is a Lucas function. It's basically a Fibonacci function with a linear factor. And there's also this strange thing called MSFIT, which I'm not going to explain, but it is an iteration that works particularly well for very strange data types that is not positive. Details you can find in the paper. So what I want to just go over is the types of these recursion combinators. So since you only need to do a recursive call, you only need the abstract operation of call to do the work. And for primitive recursion, you need a way to cast the abstract its essential type into a concrete recursive type. So you can do S of n and multiply it. And to do the course of values iteration, you can push in another operator, and to do the course of values primitive recursion, you can put all the operators together, and well, this needs yet another operator. But when you look at the types carefully, that out operator doesn't look very well, because R is a for all parametric, but how do you get all the information out of the parametric thing of f of R? It shouldn't have any structure, but you get a structure. So things using this out or course of values has different properties than other combinators, and we have kind of surveyed and looked into previous work, and the MSFIT is our own formulation, and we prove those kind of things, and they all embed into a well-known normalizing polymorphic lambda calculi. Like first two ones go to the system F omega, and there's something called fixed omega, and this should be embeddable into F omega and fixed omega, but I haven't actually written down and think about it. But I should think about it really hard. I haven't done it yet. So why do I care? Because me and some people can't play with cat very well. But I do have definite faith that F omega is strongly normalizing, and logically subset of some logically consistent calculi. So you have to believe actually. You can believe more concrete things, right? And also it's more. When you see the code, it's more closer to the programming language. But this is not the end of the story, because F omega doesn't have term indices, so we have to kind of extend the language with term indices, and there's only 5 minutes left. So basically, you just need 4 of these. You extend the kind arrows with, you can stick types in there, and that allows abstraction over indices, and I is just a special case of X, so it's just X, and you can apply type constructors to indices, and you can have for all indices. And we proved good properties about this, and the details are either you have a draft, or you'll also have a poster in there if you're coming to Copenhagen. And so, since we don't have enough time, we can just read these through. So we have a background theory, and we know how to embed these nicely behaved recursion combinaires, or logically we can say that reduction principles. And the Nax language supports them as a language feature, because we want to do, well, for efficiency, and also we want to do type inference and those kind of things better. And so let's see the code example. So this is how it looks like currently. So there's a tag, which is a real index that can be used in types. So you have a JDT of some kind of property. If you take a fixed point of this P, it becomes a proof. And proof is either tagged by E or O. That means N is even and N is odd. And you can put our type synonym of that, and you can define constructors with the name constructor as usual. And then write some kind of a lemma here. You step a proof with this iter combinator, and you write how indirect recursion works, and that proof, and it type checks, and this is a proof. And then you can go ahead and prove the obvious property that the length index lists are either even or odd. So that is basically it. And since this is too tedious, we kind of also let users to derive fixed points. And yes, that's pretty much it. And the ongoing work is basically have to do more proofs about some properties, and the future work is trying to reduce more annotations. I think kind annotations could be inferable as well, and you can't really do kind polymorphism because it's inconsistent, but maybe that polymorphism is okay. That's an idea. And also, there are some limitations in the syntax of large eliminations, and if you want to do these kind of things, we would have to think about that more. Are there any questions?
Questions? Okay.
familiar with it. Can you give like a one-sentence summary of what fixed omega is?
Fixed omega is a f omega, but at the kind you track the polarity. So if f is a type constructor taking x, you have to specify either x is covariant, contravariant, or don't care, or something like that. And also have equirecursive types.
Any other questions? So I have a question. So your aim is to have type erasure for like irrelevant terms which are only used in types.
Right. So that is explicitly marked in the squiggly.
Yeah. And is that similar to the calculus of implicit constructions by Bernardo and Veros?
Implicit calculus of
But that's probably one. Yeah.
Yes. So how we argue with the strong normalization is if you erase all this brackets and lambda i's, it becomes an f omega, so it's strong normalizing, and it is also causally consistent because it is definitely a subset of known logically consistent.
Yes. Okay. Yeah. Great. Good.
But I'm not sure if there is some kind of superset for fixed omega or that. That is what I mean by ongoing work. So has there been any implicit dependent calculi with equirecursive types? I don't know how to.
Okay, let's thank you.